Alright. Assalamualaikum warahmatullahi wabarakatuh and good evening everyone. My name is Muhammad Azri bin Muhammad Khalil, a first year third semester student in Materials Engineering from University Technology Petronas, UTP. So I'll be showing you today on how to install and download LAMMPS. So let's start by the way. So I'll just share my screen first. Okay. So first you have to search LAMMPS, so LAMMPS. So once you have searched LAMMPS, you are supposed to be hitting this part over here, so download LAMMPS. So yours maybe will appear down here, so just click on download LAMMPS and you'll be directed to this page over here. So download LAMMPS, you can download LAMMPS as a tarball and everything. So okay, you can click to the install pre-built Windows package since I am also using Windows. So you just click over here and you'll be directed here. Moving on, there's a link, as you can see. Just click it and you'll be directed to this page over here. Moving on, just scroll down and this is the explanation and all. And you can see over here, there's a part where it states installing LAMMPS on Windows. Just click latest version. And then this is the page you want to go. And as you can see over here, there's this part. Okay, so lamps-64bit-latest.exe. You can click and your download will start. Let's see. And our download will finish in around 6 minutes and I'll get back to you once it's done. So we are back and I think the download has been completed. So let's just click and supposedly your PC is actually not. What does that time mean? Okay, so just press more info and just click run anyway. Moving on, it's supposed to be running. Let's just wait. Okay, so it's loading. Okay, so yes, I have installed it before. Let's just uninstall it and uninstall. Okay, so yeah, it's done. So it's either maybe your laptop will prevent it from downloading as it's a software you are downloading from the internet and not from the computer itself. So once you have, if let's say it appears on your laptop, then you should be pressing more info and run anyway, or any way you can still run it without the PC preventing it from downloading. Once you have given the permission, you'll be directed to this license agreement. Then you may have a read if you want to, but as usual, we'll just scroll down and press I agree. So this is where you place your file location, and I'll be placing it in my C drive. So in my C drive, space available is 84 gigabytes. That's good. So let's press install. And okay, so currently it's installing. Let's wait for it to be installed. A fun fact about materials engineering. So we are the September 2025 batch, and actually we are the last batch for materials engineering in UTP. Probably they'll open it back, but yeah, once we graduate, then there'll be no materials engineering students anymore in UTP. Okay, for LAMMPS, we'll be downloading OVITO next. So LAMMPS, there's no like specific application for LAMMPS. So LAMMPS is it's installed in your laptop, but you should be using it for the command prompt. So you can use LAMMPS by using command prompt, and you can use the code itself. To visualize it, you should be using OVITO. Okay, so it's completed. So let's close. All right. No. Yes, I think I pressed it 2 times just now. Okay, so supposedly LAMMPS is installed. Okay, so done. Let's move on to OVITO next. So OVITO. Okay, so for OVITO, you just search OVITO and there's this part here. You can just press OVITO. So the LAMMPS will give you the permission to code and to actually give the conditions you would like to see how the molecules are acting, or how the molecules change after a variable is, you play with variables in the command prompt, and LAMMPS will give you the permission to do it, and you use the code to put into OVITO and to visualize it. So as you can see here, there's a video over here, and this is how you will visualize how molecules actually behave. And to download, you just press download here, and for me I use Windows, so I'll just press Windows and OVITO basic, and your download is starting. So done. OVITO basic is already installed. Okay, so I have installed it before, but just press no, next, I agree. So this is where you'll be placing your OVITO. So as I place my LAMMPS on my C drive, I'll be also placing my OVITO file in the C drive. This is the applications you are going. This is the applications in my C drive. I'll be start menu. Okay, I think we can just place it next. That components to install, and currently extracting. So the one you installed is the what do you call it? I think it's called the installer, and you have to install it from the installer. So your OVITO won't be there unless you download the installer, right? So we're currently extracting. Okay, so completing, just press finish. No, cancel. Yes, no, cancel. Yes. Okay, so supposedly your OVITO is done. Yes. So let's just see how OVITO's interface. Alright, so this is the interface for OVITO. And I think that's all from me. So I've shown you how to install LAMMPS and install OVITO. For the simulations, I'll be directing you to my friend next. Have a great day. Bye.
Thank you, Azri. My name is Hazi Aikal, and today I'm going to show you how we both simulate copper and argon using LAMMPS. So first thing first, I'm going to show you how we simulate copper. So for copper, we are going to use EAM potential so that it can show a more realistic crystal behavior. So what is EAM? EAM stands for Embedded Atomic Method. So to get the file, you need to search for it. So the address is as shown on the screen. Where you go to the address, you need to search for the file that's named cu_u3.eam. When you get the file, you need to copy it and paste it on the same location as your copper script. To activate LAMMPS, you need to use command prompts. So in the command prompts, you need to type in C column, then press enter, then type in CD space in quotation. You need to put the address where the copper script is. So yeah, you just need to copy and then paste the script and then close the quotation and then press enter. So then it can acknowledge where the folder is. So after that, to activate LAMMPS, you just need to type in LMP space -in and then space again. And then you need to copy the names of the file where the script is. After you copy and paste it in the command prompts, you press enter and then the simulation will run. After the simulation run, it will give an output file.
Alright, so as you can see here, you after you have done the simulation, using command prompt and LAMMPS, you'll have the output file. So once you have the output file, maybe you can find it somewhere in your script folder. Once you have the output file, you are supposed to drag the file, or you may just put the file, just drag it into your OVITO. And in OVITO, if let's say a simulation is running, then you have to overwrite it. If you don't have, then it's fine. So just press yes as you overwrite. I have a simulation running before. So as you can see here, this is the structure of copper. And the structure of copper is arranged in a very repeated structure, and it's called face-centered cubic. It's a crystal structure, and that's why it's repeated. And when you have a crystal structure, you are actually using the EAM as explained by Haziq just now. It's embedded atom method. So embedded atom method is a mathematical model that is used by LAMMPS to calculate how the atoms interact with each other. Since copper consists of metallic bonding, so as you know, metallic bondings consists of the sea of electrons. So they have this a vast sea of electrons. So you do have lots of things to consider. So when they share electrons, they'll create forces between each other. So EAM calculates this force, and LAMMPS is using this model to calculate how the atoms will interact with each other, and will simulate it. And as you can see, this is what happens during the simulation. I'll just play just a minute. Okay, so as you can see, the atoms are actually vibrating. And why are they not drifting away? Or it's because they have this metallic bonding, as explained just now. Besides that, as you can see, they are not still. So although it's a solid, they are not actually not moving, and they are actually vibrating at its own position. And I think that's all for copper. Let's move on to argon simulation.
So now I'm going to show you how we simulate argon. So for argon, we don't need to use any EAM files. We just need to have the script as shown on the screen. So first, we need to open the command prompts, and as same as before, we need to use C column, then press enter, then press CD space in quotation, put the address where the file is located, and then when you press enter, you get the command prompt is acknowledge where the file is. So to activate LAMMPS, you need to type in LMP space -in, and then after that you need to copy the names of the file where the script is, and then you press enter. So now the script will run and simulate how argon works. So after all the simulation, automatically the output file will be put in the same folder as your script is in.
Once we are done with this simulation, we will have the output file. Let's just drag the output file to our OVITO. And we do have the copper structure just now. And let's overwrite it. Okay. So as you can see here, it's a bit different. The structure is a bit different compared to copper just now. This is because argon is a noble gas. It's known as a noble gas, and it does have a weak interaction. So this weak interaction is called van der Waals. So for compared to copper has a metallic bonding, so it's known as a strong bond. However, for van der Waals, it's known as a weak bond. And this interaction between atoms is calculated by balancing two forces. So let's say you have two atoms, so you do have this force. When they are close to each other, they will repel, because of its nature, and when it is far apart, it's going to pull. And this balance of force is being calculated by Lennard-Jones potential, and LAMMPS will be using this mathematical model or Lennard-Jones potential to calculate F equals to ma, or second Newton law of motion, to calculate how the atom's going to behave for every run length or every time stamp. So as you can see, this is so when it calculates F equals ma, so you know the mass m, and you do calculate the force using the mathematical model you have just now. So for this, you have Lennard-Jones potential. So the acceleration is being calculated every. So for example, you have the timestamp. So this every second, every how many seconds, it will calculate how the atoms behave. So this is argon. All right, I think that's all for argon. Let's move on to changing the parameters.
So the first parameter that we are going to change is for copper, which is temperature. So we are going to choose 1000 Kelvin temperature. So to change it, we just need to change the temperature at velocity all create 300, change it to 1000, and at fixed 1 all and VT temperature 300, change it to 1000. As shown on the screen, I'm already changed it. But as same as the step before, we are going to use command prompt and then type in the addresses that the script is located in. And when we press enter, we put the names of the file. And then we run the script. After fully run the script, we can get the output in the same folder as the script. So now we are going to study the parameter changes. First, we are going to study the parameter changes for copper, and the one that we choose are the temperature parameter changes. Originally, the copper simulation was conducted at 300 kelvins. Now we are going to modify it to 1000 kelvins while keeping all other parameters constants. So to see what's changed, we are just going to take the output that we get from the simulation that we do to get the simulation that we do after we changes the parameter, and then just drag it to OVITO. I already done it, so we are going to continue with the explanation. As you can see from the OVITO visualization, it can be observed that the copper atoms at 1000 Kelvin vibrate much more vigorously compared to those at 300 kelvins. The atoms show large displacement from their equilibrium lattice position, making the crystal appear less ordered due to increased thermal motion. However, the FCC crystal structure remains generally intact because the temperature is still below the melting point of copper. This behavior can be explained through using the Maxwell-Boltzmann distribution. According to Maxwell-Boltzmann theory, increasing the temperature shifts the distribution of atomic kinetic energies toward higher values. As a result, a large fraction of copper atoms possess higher kinetic energies and move at greater velocities. The increase in kinetic energy causes stronger atomic vibration and greater atomic mobility throughout the crystal's lattice. Therefore, the increase in temperature from 300 Kelvin to 1000 Kelvin result in enhanced atomic motions, larger vibration amplitudes, and increased thermal disorder within the copper crystal, which is consistent with the prediction of the Maxwell-Boltzmann distributions. So now we are going to study the parameter changes, which is PBC. So to change the boundary to from periodic to fixed, we are going to change this line here. for boundary PPP, we are going to change to boundary FFF. So after we change it, we are going to save it, and then we are going to do the same as before, like copy the address and then press enter, and then we are going to copy the names of the script, and then to activate the lamps, we are going to do as the same as before. Type in LMP space dash in and then space and then the name of the file, and then we are going to run the script. After running the script, we are going to get the output shown on the screen. Next, we are going to continue with boundary condition PBC using copper. For the boundary condition parameter studies, the original copper simulation used periodic boundary condition, boundary PPP, and was then modified to fixed boundary condition, boundary FFF, while keeping all other parameter constants. In the simulation with periodic boundary condition, the simulation box behaves as if it is infinitely repeated in all directions. When an atom leaves one side of the simulation box, it re-enters from the opposite side. As a result, the copper crystal represents a bulk material with no exposed surface, and the atom experiences a uniform environment throughout the simulation. When the boundary condition was changed to FFF, the simulation box no longer repeated itself. The crystal now had free surface at the boundaries, causing surface atoms to experience fewer neighboring atoms compared to atoms in the inferior of the crystals. In OVITO, this can be observed as the appearance of crystal surface and edge effect that were not present in the periodic systems. During the simulation, some atoms near the boundaries gain sufficient kinetic energies to move outside the simulation box. Since fixed boundaries do not allow atoms to re-enter the box, LAMMPS reported a lost atom error. This occurred because atoms crossing the simulation boundary were removed from the systems. This behavior can be explained using boundary condition theory. Periodic boundary condition PBC are commonly used in molecular dynamics to eliminate surface effects and simulate an infinitely large material using a relatively small number of atoms. In contrast, fixed boundary condition create a finite system with exposed surface, allowing surface phenomena and atom loss to occur. Therefore, changing the boundary condition from PPP to FFF introduces surface effect, reduced the stability of boundary atoms, and resulted in atom loss from the simulation domain. So now we are going to change the parameter for argon. We are going to change the run length of the argon parameter. So to change it, we just need to rewrite the run 10,000 and change it to run 1000. After we change it, we just need to copy the addresses of the changes script, and then we are going to write the address in command prompt, and then we are going to press enter, and then we are going to enter the names of the script, and then after that we can run the script. After we run the script, we can get the output.
Alright, so we are done with copper. Now we are changing the parameters for argon. So for copper, we are actually changing the molecule itself or the atom itself to know what will happen if this changed or this changed. However, for argon, we are changing the parameters for the calculation or for LAMMPS itself. So LAMMPS is LAMMPS uses LAMMPS uses this parameters called run length and time step to determine how many times should it calculate and how long should it calculate. So let me just, earlier in this video, I told you that LAMMPS is actually using two mathematical models to, there's actually few models, but for our video, for copper, we did use EAM, embedded atom method, but for argon, we used Lennard-Jones potential. So these two mathematical models are used by LAMMPS to calculate force. And when you have force and you have mass, you can calculate second Newton's law of motion, which is F equals to ma. So you have F, you have m, you can calculate A, and by that, LAMMPS can use this calculation to determine where will the atoms go next. As you can see, the atoms are actually moving, right? So it vibrates at its own position. So to know where will the atom go here or go there, so it uses F equals to ma by using these mathematical models I have told just now. And this the original argon uses 10,000 run length. So it will finish the simulation after 10,000 times. As you can see, the frames here, as you can see, this is the current frame. Alright, let me just stop here. So you can see that it's actually 700, 800, 900. So at time step 0, it does not move anywhere. So time step 100, it moves here, and then time stop 200, it moves there, and until it reaches 10,000. So after 10,000, it will finish. So this is the last. So run length determines this. So how long will the simulation run? It is determined by run length. So for example, this is 10,000 time step. So let me just take 1,000 for example. So I have this here, run length change. So this one is 1,000 as Haziq did just now, the simulation. That's okay. So as you can see, the simulation finished faster compared to before. So this is because you only use 1,000 run length. So let me just go over here. So at time step 0, it does not move anywhere, and then time stop 100 until it reaches 1,000. Compared to just the file before, it uses 10,000. So that is for run length. So run length is to determine how long will your simulation run. Let's move on to the next parameter change.
For the last parameter that we are going to change for argon is time step. In the original script, the time step is 0.005, and we are going to change it from 0.005 to 0.001. So after you change it, you need to copy the address where the file is and go to the command prompt and type in c/cd and paste the where the address is. And when you get this, you need to copy the name of the file, type in LMP-in to activate the LAMMPS, and paste the name of the file, and the script will run. After the script has done running, we need to, and then we can get the output for the parameter change.
Alright, so as you can see here, this is the original script of argon. Okay, so we are changing the parameters of time step. So basically, what run length do is to determine how long will the simulation run. So for example, just now we did 10,000. Also, this is the same original script, so it runs for 10,000. However, for time step is how many calculations will be done for like every how many seconds. So for example, in this original script, we are doing it at 0.005. So this means that the calculations will be done at 5 femtosecond. Since LAMMPS is using picoseconds unit, so 0.005 is 5 femtoseconds. So 5 femtoseconds means it's times 5 times 10 to the power of negative 15. Okay, so the analogy is, okay, so for example, if you are taking a picture, okay, the higher frames per second, so in a second, if you have higher frames, then you'll get a more accurate picture. However, if you in a second, then okay, for example, in a second you have 50 frames, then you'll have a more accurate picture compared to 20 frames per second, because maybe in between those 20 frames you'll have moments you'll miss. Okay, so the higher frames per second is better. So for example, this one is 5 femtoseconds. So in 5 femtoseconds, it will calculate until it reaches 10,000 run length. But for example, Haziq changed just now. He changed it to 0.001. So this means that it's 1 femtosecond. So every 1 femtosecond, the calculation will be done. So in 10,000 run length, every 1 femtosecond, the calculation will be processed. However, since it will process more calculations, then the simulation will run longer. So that's basically the analogy of what time step is, and also run length. Okay, so for example, I can show you a demonstration. This is at 0.005 and this is 5 femtoseconds. You can't see much the difference. It's basically this is what happens at 0.005, also at 10,000 run length. But if, for example, then you'll take, okay, this one is time step change. So this is the output file. All right, so for example, you'll put it in OVITO. All right, yes. Okay, so this is basically, you can't see much of the difference. But however, this is a more accurate. This is more accurate compared to 5 femtoseconds. So that is how time step and run length actually determine how accurate your result will be in OVITO, in LAMMPS and also OVITO. All right, I think that's all. I think this video is, I hope this video can benefit all of you, and have a great day. Thank you so much. Bye-bye.